So now the next thing that we have to study after this electronic configuration is that there are two sets of orbitals. First, let's just practice a bit more. For vanadium 23, how would you do the electronic configuration? Yes, it's 23 electrons. 23 electrons. How would you arrange these 23 electrons? If you tend to forget, just make that diagram. Yeah. You have 2p6, 3s2. What's after 3p?
It's going to be 4s2
Yes.
and 3d.
4s2 and 3d. 3. Let's move on to chromium. Okay, there's a mistake over here. This is not the final version of your electronic configuration. What's the mistake?
The 3d and the 4s.
Yes, you have to flip the 3d and the 4s orbitals after filling the electrons. So this 4s will move out, right? And what about chromium? Chromium should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d.
3 and 4.
4.
But then we flip them.
Yes, and we flip 4s and 4s just moves out, right? But there is an additional thing that you have to consider here. This is still not correct. Okay, and you can do it for manganese yourself and for iron and for cobalt. Then there's another case of copper. How would you do the electronic configuration of copper? 1s2,
1s2, 2s2, 2p6, 3s2, 3p6, and then 3d9, and then 4s2.
3p6, 4s2, and 3d9, and then you just flip them, right? And in other cases, there's only flipping of the shells, but in these cases, there's an extra thing that we have to learn now. Okay, and that is stability. Stability of fully filled, half filled, fully filled, half filled, and partially filled subshells. You have to remember that we'll write a note that half filled and fully filled orbitals, yeah, subshells, fully filled subshells are more stable than partially filled subshells. Okay, so half filled subshell or a fully filled subshell is more stable than a partially filled subshell. So in case of an s orbital, what would be its half filled configuration? How would an s orbital be half filled? How many electrons should it have? One electron. This is the half filled arrangement. And what about fully filled? Yes, half filled means half filled means that there are half the number of electrons from the total number of electrons it can accommodate. So S could accommodate 2 electrons, half of that is 1, so half filled is 1, right? And what about fully filled? How many electrons? 2 electrons. So that means that there isn't any partially filled case for S orbital. Okay, S can never be partially filled. It can either have 1 electron or it can either have 2 electrons. That means it can either be half filled or it can either be fully filled. But what about a p orbital? So a p orbital, in order to be half filled, a p orbital can accommodate 6 electrons. What's the half filled configuration? Yep, it needs to have 3 electrons, and we always fill 3 electrons separately in their own orbitals with the same charge, right? And in the same direction. What about the fully filled configuration for the p subshell? It should have 6, right? And what about the partially filled configuration? That would be 1 electron, 2 electrons. Should I write 3 electrons in partially filled for p? Would that be a partially filled case, or would that be half filled for P? That would, yeah. So we will skip 3. It can either have 1, 2, 4, 5, and what about 6? Again, 6 is fully filled, so we skip that, right? So it can have 1 electron. This is the half filled configuration. It can have 2 electrons. It's still partially filled. What about 3 electrons? 3 electrons, it becomes half filled. What about 4 electrons? So 1, 2, 3, and 4, that would be partially filled. And what about 5? 5 would still be partially filled. So what the main point is that partially filled subshells are unstable, and half filled and fully filled subshells are stable. What about a D subshell? D has a total of 5 orbitals. So how many electrons should it have to be partially half filled? It should have 5 electrons. What about fully filled arrangement for D? It should have 10 electrons. 1, 2, 3, 4, 5. This is half filled, and then 7, 8, 9, 10. This would be the fully filled configuration. It's more stable this way. And what about partially filled? It can have how many electrons for being partially filled? It can have 1, 2, 3, 4. We skip 5, 6, 7, 8, 9. You skip 10 because that's fully filled. Right? And what about an F orbital? F should have 7 electrons to be partially filled, sorry, half filled, and 14 electrons to be fully filled. And apart from these two numbers, it can have any number of electrons to be partially filled, right? So 1, 2, 3, 4, 5, and 6. We skip 7, 8, 9, 10, 11, and 12, and 13, and we skip 14, right? So these are the number of electrons that it can have to be partially filled, right? So now in this case right here, in copper and chromium, and no other cases, by the way, only these two cases are special cases that you have to memorize this for. In chromium, you see that the 3d orbital has how many electrons? Yeah, in chromium 24. So I'm just going to move the 4s back inside. So suppose we wrote this electronic configuration 4s2 3d4. How many electrons does the 3d orbital have? It has 4 electrons, right? 1, 2, 3, and 4. And how many does the s orbital, 4s orbital, have? 2 electrons. Now you need to consider that is there any other possibility that would be a more stable electronic configuration for chromium? Yep. If 4s1 becomes or if 3d becomes a half filled orbital, it would be more stable than a partially filled 3d4 orbital, right? So stability for 3d would increase, and would the stability of 4s decrease if we remove one electron? Yeah, it also stays half filled. So what we'll do is we'll excite one electron from the 4s orbital into the 3d orbital. Now what happens is that 3d was initially partially filled, and this was partially filled, and this was fully filled. Now the next arrangement that we have decided is that both are half filled. So what would be a more stable electronic configuration? One's partially filled and one's fully filled, or both are half filled? Yeah, both half filled subshells would be more stable than the previous arrangement, right? So what we do is that we excite one electron from the 4s to the 3d orbital. So before even switching the places, what you'll do is you'll excite one electron from the 4s orbital into the 3d orbital. Okay, so what's the next electronic configuration? So this was wrong. You have to excite one electron, because by the excitation of this one single electron, you end up with a more stable electronic configuration. That's why you're doing this. Okay, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 3d 5 both end up being half filled, right? So you're still left with one thing that you still have to do. What's that? Yep, you have to flip them. In any case, you have to flip them. Whenever you see 4s and 3d together, you have to flip them. But in chromium's case, you had to have a more, you were getting a more stable electronic configuration by the excitation of electron. And remember, why did not we excite electrons over here in the previous case? Why didn't we excite any electrons on the 4s and make the 3d orbital more stable?
Because only 4s would be half-filled.
Yeah, because only 4s would be half filled and 3d would still remain partially filled. So it would not be a more stable electronic configuration. Or the other reason is that if you see the potential, that if by the excitation of one single electron you can end up with a more stable electronic configuration, you only do it at that time, right? And we cannot excite two electrons on 4s and completely make it empty, right? So we cannot excite both these electrons and make 3d5. You can only excite only one single electron, and if by that one single electron you're ending up with a more stable electronic configuration, then you do it, otherwise you don't. Okay, so in vanadium's case, even by excitation of one electron, the 3d orbital does not become a more stable orbital, or it does not become half filled or fully filled. So that's why we did not do it. We just ignored it and we moved on to flipping. So what we did was, in chromium's case, yes, partially filled is rather stable, yes.
But is because I know half-filled is more stable than partially filled, so
Yes.
is partially filled more stable than full?
No, 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 no. Partially filled, any case of partially filled would be less stable. Let's write it like this. It's less stable than half filled or fully filled. I think you're mixing partially filled with half filled.
Okay, so in any case of partially filled is less stable than half-filled.
Yes, half filled and fully filled arrangements are more stable than any case of partially filled. Okay, and in case of half filled and fully filled, who would be more stable in half filled and fully filled?
It would be half-filled?
Yeah. Why did you say half filled?
Would it be half-filled?
Yes, it should be half filled. Half filled would be still more stable than fully filled because it has unpaired electrons, right? So minimum repulsion between electrons, they're occupying their own orbital singularly. They're not paired with any other electrons, so they're not facing that much repulsion compared to the fully filled orbital that is facing repulsion in each case over here, right? So, but in your at your level,
So half-filled is
yeah,
more stable than fully filled because it doesn't, it's not fully joined together, so the
yeah,
bonds themselves
yeah. But
are
at
not
your level,
stable.
we do consider both of these as approximately equal.
Okay.
Okay. So basically, the main point is that both of these configurations would be more stable than a partially filled configuration for electrons in a subshell. Okay.
Okay.
So that's why when we saw that there's potential that with the excitation of one single electron, you could end up with a more stable arrangement. From a partially filled, you convert it to a half filled arrangement. That's why we had to excite the electron. And at the end, after excitation, what do? You flip them. After this excitation of electrons, what will you do?
We flip them.
Yep. So just flip them. So we'll write 3d5. So 3d5 and 4s1. Now in case of manganese, let's just go for iron, for example. Why didn't we do this for iron? Why isn't iron a special case? 1s2, 2s2, 2p6, this is 10, 3s2, 3p6, 4s2, that's 20, and then there's 3d6, that's 26. Now, why don't you excite one electron from 4s and make this 3d7? Because,
It will be partially filled.
yeah, it will still remain partially filled. There's no point in exciting the electron, right? So that's why we do not do this over here. What we'll do is only one thing, that we saw 4s and 3d together. 4s will go out and 3d will come inside, right? Now in case of copper, what was copper's electronic configuration? It was 3p6, 4s2, that is 20, and then there's 3d9. Now what do you see? You see a d orbital that has 9 electrons. So if you excite one electron from the 4s orbital, would it become a fully filled subshell?
No, we have to.
Yeah, about the d orbital.
Yeah.
Can you make the d orbital more stable? It's right now it's partially filled, but if you excite one single electron from the 4s orbital into the 3d, would it become a more stable or arrangement or more stable
Yes.
configuration? Yes, that is why we're doing it over here in copper's case also. Okay, so in copper's case it should be 4s1 and 3d 10, and then at the end what do you do? 4s goes out, 3d comes inside. Is that clear?
Yeah.
Okay. So now what we'll do is, did I send you the notes in the last class?
Yeah, I have them.
So we're done with electronic configuration now, and now we have to move on to ions and their electronic configuration. We're done with special cases. Just write a few notes over here.
I
Uh,
can take small notes as you told
yep.
me before.
So chromium 24 and copper 29, both are special cases in which we have to consider excitation of electron to form fully filled and half-filled orbitals, half-filled subshells. These are the only two cases that you'll consider this doing in this. Okay, no other case. For the first 30 elements, no other elements except for these two in which we have to make the excitation of electron.
And
And
you only mentioned the first 30 elements, right?
maybe for the first 35, but it doesn't it won't be hard for you now. If I ask you to do it for an element with an atomic number of 40, basically, you can still do that. You just have to follow that diagonal diagram, and you'll easily be able to fill in electrons. Okay. Um, yeah. One more note, that is, why can electron excite from 4s to a 3d orbital? Why? Why is this electron excitation possible? You know the reason, you just have to think about it. Why is it possible to excite electron from a 4s to a 3d orbital? Any thoughts about that? Do you remember that the 4s and 3d were very close to each other? And the energy gap between them was very, very, very small. So that's why
Yes.
the electron can easily excite into 3D from a 4s orbital because the energy gap between them is very small. But an electron could never excite from this orbital right here to a 4s or a 3D orbital. Because why? Because the energy difference is a lot, right? So electron excitation is not possible from the 3p orbital to a 3d orbital. But since the 4s and 3d orbitals are very close to each other, the electron can easily excite into the 3d, right? So this is the reason basically.
Okay, so this 4s is
or the energy difference between both of them is very small.
Very little.
Yeah.
Okay.
So
But after electrons
yeah.
enter 3D,
Hmm.
doesn't the energy shift becomes lower than for us?
Yes,
Or is
3D
it
does come inside, but look what happens. Let me just move this. What happens is this. The energy difference remains the same. 3D is coming inside, 4S is being pushed outwards, but the still the energy level difference is not that much. Right? Energy difference is not that much. It's still very close to each other. What happened was that 3D came inside and 4S was pushed outside. That's the only
but
thing
that
that's
means that
happening.
3D is closer, right?
Yeah,
And that means that
3D
it
comes
has
inside. Yes.
less energy. Has less energy than for us when it has the electrons.
Yes.
So then would it mean that we would then move from 3D to 4S? Or still 4S to 3D energy excitation? Or is it different?
No. First, when we are filling electrons, the electrons will automatically fill themselves according to the most stable arrangement. What we're doing is we're trying to figure out how to actually do it on paper, right? So what we did was, because 4s was closer to the nucleus, we filled it up first, and then we filled up 3D. Now if we end up with a 3D arrangement of, as a, like for example, a partially filled 3D arrangement, then we see that 3D could be stabilized by the excitation of one electron from a 4s orbital, right? So after that we do this, and then since 3D and 4s are very close to each other, they will ultimately repel each other, and then 4s will move out and 3D will come inside. Yes, that will ultimately happen every single time, right? But there's an additional thing that's happening over here, that 3D, if it got one electron from 4s, because 4s is very close and it can borrow an electron from 4s to become more stable, what it does is it borrows an electron. Now what
It
were you
borrows
asking?
an
Yeah,
electron.
yeah.
Yeah. So but then afterwards, when 4S is after 3D,
Yes,
then why doesn't 3D give electrons to 4S?
because
Because the energy
again
shift.
that would result in a less stable electronic configuration, right? That would result in a less stable electronic configuration. This is only happening in case of copper and in case of chromium. Now the 4s orbital, in other cases it is fully filled. How would it accept any electron from 3D? It can't accept any electrons, right?
Yeah.
And in case of chromium, again the 4s orbital cannot accept any electrons. It just gives electrons to the 3D orbital. But now if you say that why doesn't the 3D orbital make it fully filled, the 4s orbital fully filled, that is because if it does do that and give it the electron back to 4s, it turns out that 3D becomes unstable again.
Yeah.
Yeah, so that's why they won't do that again.
Okay.
Okay. Okay, so what was the reason? Just let's just write the energy difference between 4s and 3d is very small. Okay, now let's move on to the electronic configuration for ions. This is going to be a new thing now. So electronic configuration of ions. Now how do you do the electronic configuration for ions? One exam tip: never do the electronic configuration for an ion directly. Always do it for the neutral atom first and then just remove electrons. Okay, so this is just a tip. If you follow this, you won't make a mistake in electronic configuration. And you have to remember that do the electronic configuration for the neutral atom first, then do it, or then just remove electrons. Remove electron later or add electron later. So for example, if I say write down the electronic configuration of a sodium ion, So what you need to do is, for some time, just or for an instant, just forget about this. Act like this does not exist. The positive charge is not there. It's just a neutral atom. So if it is a neutral atom, what's the proton number? 11. How many electrons should it have if it is a neutral atom? 11, right? So 11 electrons. Now write the electronic configuration for 11 electrons. How? 1s2, 2s2, 2p6, and 3s1. Now you go back. This wasn't a neutral atom. It had a positive charge. What does 1 plus charge mean? Yep. A positive charge means it has lost one electron, right? So you just lose one electron from the outermost shell or the outermost subshell that you have. Just remove one electron from there. So this 3s electron is going to be removed, right? So this 3s is no longer over here.
So what about for
Yeah, exactly. No, we will not do that. That is the most confusing thing I know about that. So when we move on to that, I will move on to that about after 4 examples. Okay. So wait for it. This is the best tip I can give you. First do it for neutral atom, then just remove electrons. Write the most stable electronic configuration of the neutral atom and then just remove electrons from the outermost orbital. Okay. So in case of, for example, aluminium is 3 plus ion, for example, aluminium 3 plus ion. So we would forget about this charge over here. Forget about it for a second. If it was a neutral atom of aluminium, how many electrons would it have? It has 13 protons and it would have 13 electrons, right? So you need to do the electronic configuration for 13 electrons. What would it be? 1s2, 2s2, 2p6, and 3s2 and 3p1. Now what you do is consider this 3 positive charge. Now 3 plus charge means it has lost about 3 electrons. So you just start removing electrons from the outermost. So you move one electron from here, this is gone, and the remaining 2 electrons from 3s, this is also gone. So this would be the electronic configuration for an aluminium 3 plus ion, right? And what about a negative ion? For example, you have O2 minus ion. What does a negative charge mean? It has gained electrons, right? Yep. So just forget the charge for a second. How many electrons would a neutral atom of oxygen have? 8. So 1s2, 2s2, and 2p, 4. Now consider the negative charge. 2 negative means it has gained 2 electrons. So you add 2 more electrons to this electronic configuration. Where will you add these 2 more electrons? Yep, in 2p there's still space for 2 more electrons, so you just put those 2 electrons in 2p, right? It's not very hard. Now we'll move on to, for example, a transition element. Okay, let's practice one more and then we'll go to that. For example, chlorine 1735.5 and chlorine has a 1 minus charge. Yes, forget the 1 negative charge, just consider the neutral atom. How many electrons?
17.
Yep, 17. So 1s2, 2s2, 2p6, 3s2, 3p5. Now you go back and you see that this is not a neutral atom. It has 1 minus charge. That means it has gained 1 electron. So what would be the final electronic configuration? Now you have to add one more electron to this electronic configuration. So add one more electron, this becomes 3p6. So this would be the electronic configuration for the chloride ion. Now for example, let's go to scandium first, the electronic configuration of scandium. Scandium is 21 and scandium has a charge of 1 plus. Scandium is a transition element, so it can also have a charge of 2 plus. It can also have a charge of 3 plus. Depends. So what about scandium 1 plus? Again, never do it directly. Go to the neutral atom first. What's the neutral atom of scandium? How many electrons? It has 21. So you do it for 21 first, and you write the proper stable electronic configuration with all the flipping and everything. Even if there's excitation, you do the excitation. After you've written all of that, then you start removing electrons. Okay, not before you have written the complete stable electronic configuration. So for example, for scandium it is 1s2, 2s2, 2p6, 3s2, 3p6, and what about the next two electrons, 4s2, right? And one more left, that is 3d1. Now don't start removing electrons just after writing this. Yeah, don't start removing electrons just yet. What do? You consider, is this, yeah, is this the stable version of this? No. What will you do? 3d comes in. Yep. 3d1 comes in and 4s goes out. Now is this a stable version? Yep. Now you start removing electrons. Now you tell me, where would the electron be removed from first? Yep, 4s is on the outside. After the stable electronic configuration, 4s is outside. So you remove the electrons from 4s first. Okay, so scandium 1 plus, what would be the electronic configuration? 4s1. For scandium 2 plus, what would be the electronic configuration? Yep. And you'd be left with 3d1. And what about scandium 3 plus? The electron from 3d1 will also be lost, right? 3p6. 3d electron is going to be lost, right? You're considering the neutral atom and then you're removing 3 electrons from there. So how many electrons are you left with after 21 electrons minus 3 electrons? That's 18 electrons. Are you done remaining? Do you have 18 electrons remaining now? Yeah. So basically, let's just write it like this. 4s1, let me just write the neutral electronic configuration for everyone. That is 3d1 and then 4s2, right? Now what you do? For scandium 1 plus, you remove 1 electron. So that means 4s1. For scandium 2 plus, you remove 2 electrons from the neutral atom. So you remove both these electrons. For scandium 3 plus, you have to remove 3 electrons from the neutral atom. So you removed all 3 electrons. 4s electrons lost first and then the 3d electrons. Right? But if you do not want to do it like this for the ion and you want to do it directly, just memorize this note right here, that whenever transition elements form ions, the 4s electrons are lost first. Okay, just remember this note if you want to do it directly. But I do not suggest doing it directly because you will make a mistake and you do not want to make mistakes. So just, these are free marks in your paper if you have to write the electronic configuration. Just be careful with it and you score the mark. What about, for example, if we go to, what's the next example? Let's do it for let's do it for manganese 2 plus, Mn2 plus. Manganese is 25. So how would you do it? First you'll ignore this charge right here and consider this to be a neutral atom. How many electrons would a neutral manganese atom have? 25. So 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2, and then how many 3d electrons? 3d5 electrons, right? Now, should I start removing electrons? But if you want to remove electrons, what do you have to remember? 4s electrons are lost first, then you move on to the next electron, right? If you want to write it directly from here, you just remove this and you're done. Yeah, but I don't recommend that. What do? First, you write the complete stable electronic configuration And now you know that the electrons are going to be lost from the outermost subshell first. So what is the outermost subshell right now? That is the 4s. So you remove electrons from there. Okay, so both the things can work for you. Now that's all for ions basically. Okay, but we should do the copper case or chromium case because you might get confused for while you're doing it for them. But just remember one thing: you're writing the most stable form of electronic configuration for any atom, and then you're removing electrons. Okay, so even in case of copper or chromium, first you'll have. So even in case of copper or chromium, which are the special cases, you don't just start removing electrons. What do? You write the most stable electronic configuration that includes the excitation of electron and the flipping of 4s and 3d. After you're done with that, just remove the outermost electrons. Okay? So never rush it. For example, for copper is 29. What happened to my pen? Okay, I'll let you do it. For example, do it for copper 2 plus and for chromium 3 plus.
Copper 2,
3 plus, yeah. Copper has an atomic number of 29 and chromium has 24. Yeah, do it for copper 2 plus and chromium 3 plus.
for copper, instead of 1s2 plus 2 6 plus 2 6 and 34.
What was it again?
1s2, 2s2, 2p6, 3s2, 2p6 and 2p4.
Okay. What about chromium 3 plus?
R2. So I want to say for copper.
Right.
Yeah. And then for chromium, it will be 1s2 plus 2 to be 6, 2 to be 6 and 34. 3d.
That's 83. Okay, let's
Yeah.
check. For copper, first we'll have to write the neutral atom's electronic configuration. That would be the first 18 electrons till 4s2, right? The first 20 electrons till 4s2. I'm just going to write this. So when we add 4s2, then we have to fill 3d9,
No.
right? Now we see that this is not the electronic configuration which is stable. So first we have to make it stable. How do you make it stable? One thing is that you will have to flip 4s in 3D, but even before that, you see that by the jumping of one electron, the excitation of one electron, it becomes more stable. The d orbital becomes fully filled, right? So what do you do? What do you do? You excite one electron into the d orbital. Now what do you do? You switch places. So 3d10 and 4s1. Now you look at this is the neutral atom's electronic configuration. What are you going to do? You have an ion which has a 2 plus charge, so you have to remove 2 electrons, so this is correct, right? And what about chromium 3 plus? Chromium 3 plus had an electronic configuration of 4s2, that would make 20 electrons, and then 3d, 4 electrons. Now you know that this is not the stable electronic configuration, and in case of copper and chromium, you have to consider the excitation of electron, right? So one electron excites from here, you're left with 4s1, 3d5, and then you also have to flip them. Now you remove electron from the outermost shell and you have to remove how many electrons? 3 electrons. So 1 electron goes from here and 2 from the d orbital. How many are left in the d orbital? 3 are left. This is also correct. So any other confusion left in the electronic configuration part?
No. Okay.
So you're clear on this 3D and 4S thing also? Yeah. Great. So let's move on to another thing. This another electronic configuration known as the shorthand electronic configuration. So basically, in the shorthand electronic configuration, instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, and for example, yeah, 3p6, instead of writing this again and again and again, what do you do is that you replace, for example, the first 10 electrons, you'll replace it with an element or a symbol of an element from the group 8 of the periodic table that has 10 electrons. Okay? And who is that, by the way? That's neon.
That would be neon.
Yeah. So in order to skip writing this, what do? You write neon instead. Now if we do the electronic configuration of neon itself, it is 1s2, 2s2, 2p6, right? So we're just replacing this whole section of the electronic configuration with neon, right? So, and what about if I had to like replace this whole section till here, till 18 electrons? What would I do? I would replace it with argon. Argon has 18 electrons. I would write Ar instead of this, right? So I could write the electronic configuration. For example, we have zinc. So we had zinc is 30 electrons. So you write 1s2, 2s2, 2p6, 3s2, 3p6, then you go to 4s, and then you go to 3d10. These are 30 electrons. Now you know that 4s and 3d have to flip, right? So you flip, that becomes 3d10, and then that becomes 4s2. Let me just change the color. Yeah. So now, in order to write the shorthand electronic configuration, basically you're required to understand if that in the exam it's written argon and then there's 4s2 and then there's 3d10. You should know what argon is representing over there, right? So it means that the first 18 electrons have been filled. You don't need to write all those electrons. So how could I write this same electronic configuration in the shorthand form? I could replace the first 10 electrons with neon, and then I could continue with 3s2, 3p6, 3d10, and 4s2. This could be one version of the shorthand electronic configuration. Or what I could do is I could replace the first 18 electrons with whom? I could replace them with argon, and then I could continue with 3d10, 4s2. Right? And then there's also krypton, but you don't need to go to krypton. These two are the most important that you need to learn. Okay, and if you want to know where krypton is, so krypton has how many electrons? 36. Can you see 36?
36.
Yeah, in the group 8, look, it has 36 electrons. So if you have, for example, 40 electrons and you don't want to write the first 36 electrons in the 1s notation, you just write krypton and then you continue with the next, right? So, but the problem with this is that since you're not very used to the order initially, and you won't be able to pinpoint initially that where the first 10 electrons end, right? Which subshell has been filled after the first 10 electrons, so it will be hard for you to write it directly. So what you do is, for example, if you see neon in the exam, if you see neon, you write that the first 10 electrons have been filled. That means 1s2, 2s2, 2p6. So you are at 2p6, and now after 2p6, I have to write all the other electronic configuration remaining subshells.
So it's basically all gases, right?
Yep, all the group 8 elements, because they will be completely filling all of these, right? Apart from them, no other group will be completely filling these subshells. Exactly. So this is one thing. There's another way of writing the electronic configuration, and that is the energy level diagram. And what is that? I think we did we not make this in the previous class? Did I give you homework for this? No, I think I gave you the box notation and I gave you the 1s notation, right?
Yeah.
These two notations, yeah. So there's also this energy level diagram that basically represents energy levels. What do is you make an arrow, you make your nucleus over here, you label nucleus. It's basically a box plot but in vertical direction, right? So you have energy on the y-axis. What you do is you write 1s is close to the nucleus, so 1s2, and you label it. Then you're at 2s, 2 has more energy than 1s, right? Then you move on to after 2s, what comes after 2s? 2p, right? So 2p has even more energy, it is higher in energy. So 2p6, for example, this is 2p. And then what about 3s? 3s would have is even further from the nucleus and higher energy. So what is happening on the y-axis? Look at the y-axis. What is happening? Energy is increasing. But what do you say that what about these three p orbitals? Three orbitals in this p subshell. They all have the same energy. What do you call the same energy orbitals? You call them degenerate orbitals, right? They all have the same energy. But 2s or 1s aren't your degenerate orbitals, right? So let's just move on. For example, this is 3s, and then you move on to 3p, then you move on to 4s, then you move on to 3d, and again in the 3d orbital there are 3d subshell, there are 5 orbitals which are degenerate, which are the same energy level, right?
Yeah.
So basically this is the energy diagram. And even in this, if the 4s and 3d are filled and they are together, what you do in the end is, what do? You flip them. You flip them at the end. Now what do you see happening? And after this flipping, 4s went to higher energy and 3d came to lower energy because it came closer to the nucleus, like we said before. Clear? Okay. So what's next? What's next? Yeah. Now what I want you to do is, I need you to, and it should be handwritten. I need everything handwritten. I don't need any PDFs, any Word documents, nothing. I need everything handwritten form. Even if I send you the topical, you have to do it on your iPad with your what do you call the iPad pencil?
Apple Pencil.
Yeah, Apple Pencil. Yeah, you have to do it with your Apple Pencil on the iPad. You have to write everything with your hands, and you need to send me that version.
Do
Yeah.
it on paper as well.
Sorry.
That's fine. On paper is fine as well, right?
Yeah, on paper is fine as well. Yes. But I think if I send you a document that you have to solve, right? If I send you a topical, wouldn't that be easier if you just do it on my iPad? You just open it over there, and like I've opened this notes app. I solve papers over here like this. See, I've solved every single paper on this. Here. So I think this would be an easier approach. But if you want to like print it out and you want to do it with your hands, that's also fine. Okay, handwritten is also fine. Now what I want you to do is I want you to do this energy level diagram again for the first, should I say 30? Would that be too much? Okay, first 30 elements. Okay, first 30 elements you have to do the energy diagram, and then even the stable electron configuration. Okay, everything should be the same, but the only difference is that you're going upwards. Now our next topic is basically the electronic configuration. Everything ends here. Now what you need to remember is how did we yeah, there's one more thing. Yeah, and it's in the start of these notes basically, where we revised O levels. Yeah, if we pass these subatomic particles or beams of these subatomic particles in an electric field, what would happen? Do you remember the alpha particle scattering experiment? Have you heard of it?
Yeah, I think I know.
Yeah. So basically, how did we know that the electron is negatively charged, the proton is positively charged, and the neutron has no charge? So basically, what we did was we placed two parallel plates. One had a positive charge, one had a negative charge. So one was acting as an anode and one was acting at like a cathode, right? So what we did was we passed the beam of subatomic particles, beam of subatomic particles, and there is this gold film right in front of you. This is a gold film, okay, a thin film of gold. So what is going to happen is that these subatomic particles are going to pass through this electric field, and then they're going to strike the gold film right in front of them. So when the neutron is going, let's talk about the neutron first. We'll select a color for the neutron. This is the neutron. When the neutron passes through this electric field, does the positive or a negative change? Yeah. Does the positive or the negatively charged plate attract the neutron? It does not. It travels straight through. Right? This is the path followed by the neutron. That's how we know that neither the positive terminal or the negative terminal attracted this particle, which means this particle must be,
Zero charge.
yeah, it should not have any charge. It is neutral, right? But then another particle that went through this electric field, and then I'm going to label this with the green color, was attracted towards the negative charge, and it did not travel straight. It was bent. Its path was bent.
That's slightly, right?
Yep, slightly, yeah. Slightly bent part. How do you know it is a proton? Because it was attracted by the negative plate. That means this subatomic particle must have a positive charge.
Positive.
Yep.
Yeah.
So what is this? This is the proton. It is a positively charged subatomic particle. And in case of the electron, let's go with red for electron. When the electron was traveling, it will also be deflected.
But more, right?
Yeah, we will discuss that. We will discuss that. But it was deflected upwards towards the positive terminal. What does that mean? The electron is negatively charged. But since the proton and electron, let's compare the masses of both of them. Who has significant mass and who has negligible mass? Electrons have negligible mass, right? And protons have significant mass. They have 1 AMU, and electron is basically 1 AMU divided by 1837, and that one part of it is the mass of an electron. So basically, electron is lighter and proton is heavier, right?
Yeah.
So what happens is that the path of the electron deviates more or is bent more because the electron is lighter, right? So the positively charged terminal can attract the electron more easily. It can bend the path of the electron more easily. Because the electron is lighter, it will deviate more. But the proton being heavier, the heavier particle, if you want to bend it more, you have to apply a stronger electric field, right? So the proton being heavier did not deviate more than the electron because the electron was lighter, it deviated more, right? So what we could say is that this angle of deviation over here, we can call this 1, and this angle of deviation we can call this 2. So what would we say? That basically theta 1 is greater than theta 2. Why is theta 1 greater than theta 2? Because the electron is lighter, it deviates more in the electric field. Clear? Okay. So that's all for electronic configuration. You're still left with the second part, the second whole topic of atomic structure. That's ionization energy, right? So atomic structure is just not just electronic configuration. It's include what you'll study with it is the ionization energy. That's the second topic that we have to start. But for today, because it is 1:07, and I don't think again that we have a lot of time. So what I'll do is we'll watch that animation. Do you remember the shapes of SPD? Sorry, S and P, right? What was the shape of S orbital? It was a circle, right? It was a circle? No, it is never a circle. It is a 3D shape. It is sphere. Yeah, it is should be. You should always say it's a sphere. It's never a circle.
I said it was spherical.
Yep. You said it was a circle?
No, I said it was spherical.
Okay, spherical. Yeah. So this video right here. Now just look at the shapes and everything. Well, that's all you have to do for today. And in tomorrow's class, we'll start ionization energy. Okay. So let's just watch this for now. Now this is scandium, by the way. Okay. We just did the electronic configuration of scandium. What was the electronic configuration of scandium on your fingertips? Just say it on your fingertips. That is 1s2, 2s2, 2p6, 3s2, 3p6. Yeah, 3d1, right? And 3d1 comes inside and 4s2 goes outside after the filling of electrons, right? But in this case, let's see what happens. Okay. So this is the axis, by the way. Wait, this is the axis. What do you see coming towards the axis? The axis, the intersection point of this axis represents the nucleus. Okay, the intersection point is representing your nucleus, where the X, Y, Z axes are meeting. That's the nucleus. What do you see coming first? I wish this gets removed from it. Yeah. What do you see coming first? That was the 1s. Now, what's the size difference between 1s and 2s? Yeah, 2s is larger, right? Yep, exactly. Same shape, same spherical shape, but it is larger in size. Now you look, what is that? Yeah, so that is a P. What comes after 2s? It should be a 2p. And P has 3 orbitals, right? That's px, py, and pz. We'll see which one is this. This is the px. Red axis is the x-axis. So it is going to arrange itself on the red axis. Now 2py is coming. The same shape, same size. Just what's the difference? That it is along the y-axis. What difference? Again, it's 2pz. Now we're done with the 3p orbitals. Now what comes after 2p? That's the 3s. Do you see the size difference? From 1s to s2p is greater than all of them. What comes after 3s? That's 3p. Again a dumbbell shape. And what do you see the size difference of 3p and a 2p?
Yes.
Substrate, right? The 3p is supposed to be bigger, a bigger dumbbell shape. So that is the 3p. That's the 3pz. Now what came after the 3p orbital?
4s.
That's the 4s, and it is larger than any other s orbital that came before it, or the p orbitals that came before it, right? Now after 3p, sorry, after 3p, we saw 4s came, right? And after 4s, which subshell comes? 3d, right? So these are the d orbitals. You don't need to memorize the shapes of d orbitals, but just see that after 4s, the 3d orbital is going to arrange itself. And there's 5 different orbitals in the d, okay? And they are basically going to arrange themselves. There's this dz square, this is dx square y square. It's going to be in between, or sorry, along the x and y axis, double dumbbell shape. Yeah, double dumbbell shape. And there's this dxy which is going to arrange itself in between the x and y axis, not along it. There's dxz which is going to arrange itself in between the x and z axis, not along these axes. And then there's the yz which is going to again arrange itself y and z axis in between these axes, not along these axes. Okay, that's all we need to see. Do you want to see it again? Yeah. So just the size difference between 1s and 2s, and then the 3p orbitals that arrange themselves along the axis, the shapes, and then how the size of the s orbital is increasing, how the size of the p orbital is going to increase. Okay, that's the only 2 orbitals that you need to know.